All right, so this is meant to be our brief introduction to electrostatic forces and fields. The first of what I would consider to be two of the more difficult units that we're going to do all year. Now, again, I don't think that these two units are historically so difficult because of the content. There's no significantly more difficult math. There is no significantly more difficult, conceptual understandings that we need to have. I think a lot of it in the last 10 years I've been doing this come down to vocabulary. This vocabulary for this particular chapter, these particular sections, isn't something that you would normally use in an everyday conversation. Whether or not you're using it correctly in terms of physics or not, we're all familiar with the word force and momentum and, maybe even just energy in general in terms of, hey, I'm out of energy for today, I'm tired, or the amount of power that we have in our cell phones, things like that. But these vocab terms that we're using for electrostatics, the electrical potential differences or electric field strengths, these symbols and vocab terms are new to most of us. And I think that's where the disconnect really comes from primarily. To that end, I did incorporate, and I want to point this out. I pointed this out in class. I'll point it out again here in case you are one of the individuals not in class or are watching this again. This box down here on the main cover page of the unit packet for Unit 10, I give you every single vocab term, its symbol, and the units we use for it, along with the definitions. So if you're reading a problem in this chapter more than others, because other chapters, you have a rough understanding of what mass should be or what speed is or velocity, right? That's usually the letter V. This unit's going to be different. We've got a Q describing charges. We have a physical constant for Coulomb's constant as a letter K. Electrical field strengths are a capital E. The V shows up again as electrical potential difference down at the bottom. And so this unit is the first unit where these things really are kind of foreign to the vast majority of us, unless you or your parents have some background in electronics or electrical engineering or an electrician or whatever. To most of us, myself included when I was your age, this is going to be pretty foreign. And so this box right here is pretty much the reason why I started doing the unit packets. I wanted to give you an organized place where those units and those variables and their units can be found. That way we can come back, reference this, and make sense of the practice problems that we're going to have to do. So that was the goal. That's at least the intention behind those sheets. So please use them, absolutely. So let's talk about some of those vocab terms and what some of this means. Chapter 20, Section 1 actually isn't part of your reading notes quiz for this unit, which is coming up in a couple of days, because the book, in my opinion, takes too long to explain things that we should already know. You learned all of this either in chemistry last year or personal experiences as a kid or junior high science classes when you were playing with magnets. So we already know a lot of these pieces. And so that's what I'm going to jump into first. Electrostatics is the study of charged particles. And there are only, as far as we're concerned, either from last year in chemistry or high school in general. We're not going to get into the smaller particles that make up these guys that we're talking about, but the smallest particles we've talked about so far are protons, neutrons, and electrons, right? And so we're talking about those charged particles, those positive and negatively charged particles being held in place, collected, or stored. Hence the root word static or stationary being in there, right? We're interested in these things staying in one location and not moving about. We'll talk about electrical current next. That's Unit 11. So in Unit 10, we're talking about stationary charges. What are charges? What are some of the properties that these charges have? How do these charges interact? That's it. What is it that's actually making these charges that we experience and that we feel? That's the other part of the word, right? The other root word, going back to your reading seminar class freshman year, this is all coming from electrons. So anytime we talk about electronics, we talk about electrical current, we talk about electrostatics, we talk about an electrician or electrical power outages, whatever, we're always talking about the electron. It is always the electron that moves. I mentioned this in class, and I'm going to write it again here. The protons and neutrons stay in the nucleus. Right? From chemistry last year, you've got your nucleus with your positive charges and your neutrons all located in that one very dense little spot. And then the other 99% of the atom is regions of space outside the nucleus where the electron can exist. And the exchanging of those electrons, the sharing of those electrons is what gave you in chemistry last year your ionic and your covalent bonding. And each atom had a different number of electrons that it could share or it could take or it could give. And that's what gave us all of our different charges and all that good stuff. But my point is, protons and neutrons stayed in the nucleus. They didn't move. If protons and neutrons are moving, you have radiation. Nuclear radiation, literally, because it's coming from the nucleus. And usually it's not going to bother you, like bananas are radioactive. Potassium, whatever it is, I want to say 39, but this is a video, so don't quote me on it. My periodic table's on the back side of the room, and I don't have my glasses on. My point is that protons and neutrons are going to stay in the nucleus. So even if your nucleus is unstable, you can have them moving, sure, but that's not what we're referring to here. That's a nuclear decay process. We're talking about the movement of electrons, those little guys outside, which is why the electron, electronics is always the root word that we're using. We're talking about the motion of the electron. So gaining electrons, because electrons have that negative charge, will give an ion a negative charge, right? We talked about that in chemistry last year. Maybe not we. I probably didn't have you in chemistry last year. I haven't taught it in a few years, but go back to your periodic tables. And in those periodic tables, we should recall that there are different kinds of elements. They're all trying to have noble gas configurations. They all want to have 8 electrons in their valence shell. And fluorine has 7 of those 8, so it gains 1 to look like neon. Chlorine has 7 of those 8, so it gains 1 to look like argon. Bromine gains 1 to look like krypton. And they all get that -1 charge that was up in the upper right-hand corner of the periodic table for you guys last year, right? Oxygen has 6. It needs 8, so it picks up 2. Nitrogen needs 3 because it has 5, and so it picks up 3 more. And those charges always represented the number of electrons these nonmetals on the far right-hand side would gain to get to that noble gas configuration. The opposite is also true. If you had 1 of your 8 valence electrons, you're going to lose the one that you have because it's easier to lose 1 than pick up 7 more. And so that's what sodium did. Was potassium 39? No, it was, well, its mass might have been. Let's look. It's going to bug me. Ha ha ha, I was right. Cool, that doesn't happen often. Anyways, here's the video I'm making. So, as you gain electrons, you gain a negative charge. All objects, it doesn't have to be an atom, right? The comparison I'm making to this is chemistry last year. You did talk about it. We are not going to do those charged particles and crisscrossing charges to write new compounds. We're not doing that again. But the main idea of picking up electrons giving you a negative charge still holds true. The main idea of losing electrons giving you a positive charge still holds true. I'm going to say this right now. This is a test question. On the last exam, when I said, hey, this is a test question, machines do not change the amount of work you put in. Work is proportional to the amount of energy an object has. You can't create energy. And I said, hey, this is a test question, put a star next to it. And then on the exam, 10% of us got it correct. This is another one. When you get positively charged, when you gain that positive charge, you don't pick up more protons. That is an answer choice on the exam. You do not gain protons. You lose electrons. It's always the motion of those electrons. Protons and neutrons stay in the nucleus. So you can get a negative charge on an object by picking up extra electrons, and you can get a positive charge on an object by losing electrons. Those are the 2 ways those things happen. The next thing that the chapter talks about is your main idea from junior high science, right? We can talk about this with magnets. And if you want a weird little memory cue for this, remember the Valentine's Day grossness of opposites attract. The same was true for magnets. You know, even if you're just pulling a refrigerator magnet off of your refrigerator, you've got the two north ends, you try to push them together, the like charges will repel one another. They don't want to be near each other because they have the same charge. They have the same version of a magnetic field. We'll talk about that a little bit later. But they repel because they're the same side of the magnet. Then when you flip one of those magnets over, the opposite sides attract and they stick together. And that's just always kind of been a thing. So the book spends a long time going over all of that. Again, if you want to read it, go for it. It's chapter 20, section 1. But most of us understood, at least, or remembered that, even if you've just heard it. I know all of us have heard it at least once. Neutral objects are neutral because they have equal amounts of positive and negative charges, right? You're not going to have no positive and negative charges. That would mean you have no protons or electrons. You're all neutrons, and matter like that just simply can't exist in terms of life. Sure, we have neutron stars that are nothing but neutrons, but there's no life there to speak of that we know of. Anyways, so equal amounts of positive and negative charges is what gives you a neutral object. That is going to be a concept we're going to be using a lot of, so make sure we have that. Insulators and conductors are then the next two things that the chapter really goes over, and these are like the five only important things from all of chapter 20, section 1, which is why I want to go over them. The book spends 8 pages on this, or something ridiculously unnecessary, so I was trying to boil it down. Most of this we already knew. Insulators like thermal insulators, the issue Texas is having right now is that their homes weren't required to have thermal insulation in a lot of cases. And when it got super cold, everything is freezing and you get burst pipes and all of that other stuff, right? So thermal insulation prevents heat from leaving your home, literally. And electrical insulators do the same thing. They're made out of materials that do not allow that charge to easily move. So it's materials in which charge cannot easily flow or move. Good examples of this would be plastic. Plastic's a great insulator. Glass is a great insulator. Rubber. Anytime you see a mad scientist sort of movie, usually they're wearing rubber gloves. And so all of those rubber, glass, plastics, they're all made from non-metals. Usually carbon or silicone or phosphorus-based, nitrogen-based sort of things. But again, go back to your periodic tables, and you've got those non-metals. It's your nitrogens, your oxygens, your carbons, your sulfurs, and all of those different things that make up, where was the better picture of it? Here was the better picture of it. It's all of these guys over here that already had your negative charges. They did a good job of holding on to the electrons they had. And so when electrons, literally what electricity is moving electrons, try to go through a non-metal, well, those non-metals do a really good job at holding onto their electrons. And so they'll pick up those extra electrons and they won't let that charge easily move through them. They do a really good job of holding onto electrons. And that's the main idea. Conductors are the exact opposite. Conductors are materials through which charge can easily flow, and these are typically made out of metals. Now, going back to chemistry, remember, these metals are the things that do not hold on to their charges very well. Everything in the first column lost one of its 8 electrons in order to get that octet, right? It only had 1. It needed 7 more to get to 8 in its valence shell. So just drop the 1 and you're at the lower valence shell before it. Even your transition metals right here in the middle. These are the things we actually use for our conductive materials these days. You've got copper. Copper is the metal inside all of your wires for your laptops, for your power cables on your televisions, for your cell phone chargers, the walls in your home, all of it, right? Silver and gold are actually better conductors, and we use them in more sophisticated electronics like computer chips or some of the space probes that we use because they're better conductors. They just happen to also be really, really, really rare and expensive. So we don't line our walls inside of our homes with them, right? I'm sure Apple probably has a version of a charging wire that's made out of pure gold for the uber rich to purchase, and they'll pay you a special premium because Apple's all about making extra money. But my point is, metals do not hold on to those electrons very easily. They gave them away very easily last year in chemistry. And they still do. Metals conduct electricity. Those electrons are able to move. Remember, it's not protons and it's not neutrons that are moving. It's the electrons that orbit that nucleus around the outside that are allowed to move. That's why we call it electricity. Things don't always have to be permanent insulators and conductors. You remember you had metals in chemistry, you had non-metals in chemistry, and you had those weird metalloids, the things that like sometimes acted like a metal and sometimes acted like a non-metal and were really weird to try and classify. There are examples of this, right? The air, the atmosphere that you're breathing right now is a good example of this. Typically, it's an insulator. Your electrical outlets right now, unless you're at my home where my 2-year-old runs around and tries to stick her finger in them, are probably open and exposed to the air, and they're not conducting electricity throughout your room. The electricity is staying in those metal contraptions, right? Inside the metal wires and the metal prongs and plugs that are inside your outlets. But if you have a sufficient level of charge, those electrons can jump from one object to another, right? Yourself to your dog, yourself to the doorknob, whatever it might be. That jump we literally call a spark. This is how spark plugs in your car are designed to work. One end of that plug builds up a large static charge, and then it jumps from one end of the plug to the other, and it just happens to jump through volatile fuel, and the fuel combusts and explodes, and it propels your car forward, and it's really kind of cool, unless you have a diesel. But that jumping of electrons is your spark. Scale it up a few billion times, and you do get lightning. Right? The atmosphere doesn't easily conduct electricity, but occasionally it can if you build up a sufficient charge. So, main idea from chapter 20, section 1, losing electrons gives you a positive charge, right? You don't gain protons. Like charges repel, opposites attract. Neutral objects means that you have equal numbers of positives and negatives. Insulators don't conduct electricity, conductors do conduct electricity. And then there's like stuff that can do both, but it takes a lot of electrical charge to do it. That was chapter 20, section 1. That's the main idea. So, book spent a long time going over that. I wanted to do it real quick in a single page. Moving on from there, we get chapter 20, section 2. This is the start of your reading note quiz for this unit. So, electrostatic forces. Just like any other kind of interaction, right? If we've got things repelling or things attracting one another, then there's got to be a force that causes that repulsion or causes that attraction. Things don't accelerate by themselves. It is not the natural tendency of an object to accelerate. That was Newton's first law. Things only accelerate when acted upon by an outside force. So, for attraction or repulsion to exist, whether we're talking about magnets or your hair standing up on end when you rub a balloon on your hair, or just in general right now because it's super dry out, those electrostatic forces are the cause of that repulsion or that attraction, right? Even just the static electricity in your clothes in the winter is a force acting on your clothing, forcing it, literally, to kind of be connected to you. And so these electrostatic forces are the result of a, no, not a D, finishing the word before I began writing it, a buildup of charge on an object, and this is what causes that attraction or repulsion. We classify it, or quantify it, with an equation that we call Coulomb's law. It's named after a scientist several years ago, a couple hundred probably at this point, who was doing some of the pioneering research in it. The book put all of this in that big tan box that they always do. And it's always a really good idea not just to write down the equation, but if you were to just write on your equation card right now, F equals KQQ over R squared, you would have no idea what force we're talking about, what the heck K is, what those two Q's represent. You'd probably recognize the letter F for force or the letter R for radius, but you wouldn't know what force we're talking about. And the radius is the distance between two things, but you wouldn't know what two things we're talking about because you didn't know what the Q's stood for. So the box does give you that equation in words. It's always a really good idea to start making note of what that means. Coulomb's law in general is the magnitude of force between two charged particles separated by some distance. It is directly proportional, meaning we have multiplication of the magnitude. I'm going to do this because some of us get scared of the word magnitude despite it being in our first reading notes quiz. It's just the size of those charges. What are those charges? These are your Q's. right? Go back to the cover page of Unit 10, and I explicitly write charge, parentheses, Q, because that's the symbol we use to describe charge, just like mass was a little m, or F's or force. It's a quantity of charge, and it's directly proportional to the product of those two charges. You multiply the two of them. And it is inversely proportional, because we're dividing, to the square of the distance between those charges. This should look eerily familiar. This is identical, ironically enough, to Newton's universal law of gravitation. Why these two equations happen to be the exact same? We just substitute a universal constant and substitute charges for mass. I've never heard a good explanation, right? This isn't something that we designed as scientists because we wanted the world to work this way. We looked at planets. One group of scientists was looking at planets, Newton and a few others were looking at planets and how they moved, and they realized that they move this way. Gravitational forces act this way based on the charts and graphs and trends in their data that they observed. And a separate group of scientists were looking at charged particles, and this was the trend that they noticed and observed in the motions of those charged particles. Why charged particles and the electric fields that they make, which we'll talk about in a second, act the same way as objects with mass and the gravitational fields that they have. Why they act the same way mathematically, algebraically, I've not heard a good compelling argument for it. In fact, the vast majority of scientific professors or people that I work with in general over the last 5 schools I've taught at, this is one of those places where they like to insert religion, right? There's this misconception that science and religion can't work together, and the vast majority of science teachers I've had or worked with are very religious for weird reasons like this. There's no reason they should be the same, yet that's just what we observe. It's a really, really, really cool coincidence, and I just like pointing out, number one, science and religion don't have to be mutually exclusive, but number two, we've done this equation before, right? Yeah, we're inserting a new charge. Yes, we're inserting a new universal constant, but when we go to do the mathematics, we've done this before. This is the same as Unit 7, gravitation. So, how do these objects become charged? Again, they gain or lose electrons. You do not gain or lose protons. That's a test question, just like the last one that only 10% of us got right. Here it is written again. You gain or lose protons, or electrons. You gain electrons, you get a negative charge. You lose electrons, you get a positive charge. Multiple ways you could this could happen. It could be charged by conduction, where they physically come into contact with one another. Again, conduction, root words, conduction and contact, or charging by induction is another way that this could happen, inducing a charge. The book goes through a very, very long, detailed explanation of what charging by induction could be. I like to do it here. Basic idea is that at the beginning, you have equal numbers of positive and negative charges on an object, on a surface. You bring a charged object near that, and the way they draw it here, because physicists are annoying sometimes, they show it as like the positive charges all lining up on one side. They really don't. The positive charges are locked in the nucleus. They stay where they're at, but the electrons, when this negative charge shows up, the electrons peace out. Like charges repel. It's why you had all those molecular shapes that you talked about last year in chemistry, your tetrahedral, trigonoplanar, all of those shapes that you discussed had those shapes based on the number of electrons that were around it, because electrons would like to get as far away from each other as possible. And when you charge by induction, you move those electrons to a different part of your surface temporarily, but you can separate that surface, cut it in half, if you will. And by separating these two spheres, you basically stranded, kind of like a cruise ship, leaving you in, I don't know, Costa Maya, because you hung out too long on one of your excursions and they didn't make it back to the boat in time. They'll just leave you. That didn't happen to me, but I did watch someone get left. They were trying to chase the cruise ship one time. It was kind of funny, but also I kind of felt really bad. My point is, here, the electrons migrated, the protons did not. The electrons migrated to sphere B because of the negative charge on that balloon or whatever it was that was introduced. And when you separated these two spheres, the negative charges, the electrons, were just stuck over there on sphere B. They didn't have a chance to come back. And so now you've got two charged spheres, and you did so without making physical contact. That is charging by induction. When we do the Van de Graaff generator in class, you'll feel a charge by induction. Just if you walk next to or near the Van de Graaff generator, you will feel that electrical field and a little bit of a charge. Your hair will stand on end. It'll be pretty cool. The next chapter, so charging by conduction and induction was the main idea of chapter 20, section 2. The next chapter gets to electrical fields, right? We've talked about electrical forces. Well, if a force is being exerted on one object or another, kind of like a gravitational force, then there should be a field that is causing those forces to be exerted, right? The Earth's gravitational field causes the pen to fall, causes me to fall out of windows. Remember that one time I jumped off my balcony? I told you guys that story when we talked about gravity initially, because it's really fast. But the forces, gravitational forces exerted on you are from the Earth's gravitational field. That was the way Newton described it. We've updated that with Einstein since then, but that's the idea. And it turns out that these electrical charges have the same sort of interactions, trends. They also contain electric fields around them. Now, we draw these electric fields in one very specific way, so that there is a convention. There is a similarity between different groups of scientists, different parts of the world. Positive charges we have just come to represent as their arrows for their electric fields always being pointed outward. Right? We always use a small little positive test charge. Is the way we describe it in physics. So we insert a positive test charge. What direction would that positive test charge move? That's the direction the electric field is in, right? And since positive test charges would be repelled by a like charge, we draw the arrows extending outward from a positive charge. And it would be attracted to a negative charge, because opposites attract. We draw the electric field lines for a negatively charged particle as inward, because we're always using small little positive test charges. It's just the convention that we came up with a long time ago. So the negative field or negative charged field lines always extend inward, and the positives are outward. Just like just like gravitational fields, the Earth having acceleration due to gravity, or the fancy way of saying it was a gravitational field strength of 10 meters per second squared, we can calculate and quantify electric field strengths based on how quickly it causes those charged particles to move. It's the same idea as masses in the Earth's gravitational field. It can be observed. Yeah, sorry, I already said this one. I didn't realize I was filling in the blank when I said it. It's just what the blank should be, right? How does that charged particle move within that field? And how abruptly it moves, how quickly it moves, how aggressively it moves will tell you how strong that field is. You can have weak fields, you can have strong fields. Just like small planets from our Planet Jump Lab had weak gravitational fields, and larger planets had stronger gravitational fields. You can have strong and weak electric fields as well. Well, we're going to do the Van de Graaff here in a little bit, so it'll be a couple of days, because we're doing half students each day. It'll be in 4 days for us right now, but we will talk about those electrical field lines, and you'll be able to actually see them. It's pretty cool. So the strength of an electric field is equal to the force on a charge divided by the quantity of the charge that is there, right? Divided by the charge of the particle that is present. And because it's a force divided by a charge, its units are a Newton per coulomb. So please don't look at Newtons per coulomb in our problems that I would give you guys and think to yourself, well, I see a coulomb, so it's clearly an electrical charge. Or I see a Newton, it's clearly an electrical force. Electrical fields have units of both. So if you see a Newton divided by a coulomb, then we're talking about a force divided by a charge, and that is your electric field strength. I don't know why I'm writing it. It's right above it. I could just underline it. There you go. The next main vocab term that we're going to get to, right, because electrical field strength was an equation that we can discuss, use to describe how strong these electrical fields are, how intense they are, is electrical potential difference. And this is actually a direct result of electrical fields existing, and that word potential is put in there intentionally. Just like the Earth's gravitational field creates gravitational potential energy from literally our last unit. As you move a ball further up into the air, you increase the amount of potential energy it had. Remember, your equation for potential energy was mgh, mass multiplied by the gravitational field strength multiplied by your height above it. Well, we can calculate from that. Remember, this was your force on it. It was your weight of the object. We can do that with electric potential energy. Electric potential energy would also increase the further away you get it. We do this by measuring the amount of work, or remember, work was proportional to energy, so it's measured in joules still, divided by the charge of the object. So it's defined as the work required, which we just got done talking about in Unit 9, the work required to move a charge. And that electrical potential difference is going to be measured in a joule per coulomb, or what we now call a volt. Maybe you've heard of volts when you hear of the storage capacity of a battery, or the amount of potential, literally, the amount of potential that your electrical outlets can supply. I think here in America, I haven't looked it up in a long, I haven't talked about this in a year. We run a 120 volt system. I'm 99%. Yeah, we run 120. Europe runs a 220. But it's the amount of potential, the amount of stored energy or capacity to produce a change in the world around it that those electrons inside that circuit have. This equation works for, and this is a key part, single point charges. So if we're dealing with a single point charge, all of these equations that we've talked about so far are perfectly valid. We can use them. And this is what we'll start with. That isn't the only kind of charge that we can have. It's the most common, sure, but because these aren't planets, these are really small, we can also, for experimentation purposes, make what we call uniform electric fields. These uniform electric fields allow us to see how charged particles will move in an environment where the electrical field strength remains the same at every position. So we can measure other variables. That's the idea. The electric field strength does not fluctuate or change at all in between them. You've got one metal plate up top that's positively charged, one metal plate that's negatively charged. Remember, electric field lines are always drawn leaving a positive charge, heading towards a negative charge. That's what we just got done talking about on the previous slide, or the previous page. These are our slides. And we can calculate the electrical potential inside a uniform field. It is still calculated using work, because these fields can produce a change in the world around them, and because it's a measure of work, remember, it's a force multiplied by a distance as well. And so we can incorporate our charge there, rearrange the equation a little bit. The book does this rewriting for us. But remember, if you've got a force divided by a charge, that is the strength of your electric field. And so delta V is equal to ED is another perfectly valid equation for a uniform electric field. Not a single point, but a uniform electric field. I will always use the term uniform electric field. In fact, on your equation card, I am going to encourage you to separate these and make it like a little heading. Single point, uniform field. And I'll always use one of those two words. So it should make it a little bit more straightforward. Why are we even talking about these uniform electric fields? We're talking about them because, let me finish this. We already talked about it. We're talking about it because this is probably one of the single best experiments that we've ever done as a species. Robert Millikan, ironically enough, I did some research. This is not the guy that Millikan University is named after. It's spelled completely differently, which is a little upsetting. But my point here is that this is one of the best experiments that we have ever done using electric fields, and it led to the discovery of how much electrical charge an electron actually has. It told us the exact quantity of charge that fundamental building block of the universe contains. And so this answered a lot of questions after we figured out exactly how much that charge really was. Millikan knew and this is not going to be something that you'll be tested on. We will do a calculation similar to what he did, but you just have to know who he was and what he did, what he found, and what the number was. So Millikan knew that electrical fields could exert forces on objects. A push, a pull, whatever. Gravitational forces were something that were known about at this time as well. His goal was to attempt to measure the charge of a particle, of an electron, ideally, using the idea that these fields could exert forces. He hoped to be the first individual, and he was eventually, to discover the fundamental charge of an electron. How did he go about doing this? It's one of the coolest things that I've ever seen, honestly. He used an oil droplet. Literally, he took oil, sprayed it out of what is now something we would call a spray paint can. In doing so, leaving at that really high velocity, all of those individual charged particles, droplets of oil get charged as they pass through the spray can. And just because of the friction that they're undergoing, just leaving, they pick up a little bit of a charge. And his goal was to dial in the electrical field strength of the two charged parallel plates that he was using. I'll post a video, a video that will show you exactly what it was he was doing. His goal was to have the electric field strength in between those two parallel plates at the correct value. He manipulated it until the electrical force being exerted on the object, the force of electrostatic attraction or repulsion, which in this point is pointed up, was equal and opposite to the weight. There's our equal and opposite. It was equal and opposite to the weight of the droplet itself. He literally got this oil droplet to hover in midair in between these two charged parallel plates if he was able to get the electrical field strength at the right value. Because if this isn't pushing up enough, then the weight vector is going to win and it's going to fall, right? Where there's a net force, things move in the direction of the net force. So he had to get that upward electrical force at the same magnitude as the weight of the droplet. He did this several times, and by combining the two equations, he was able to figure out the equation just by dividing by E, right? On this side, you divide by E to get it out of there. You divide by E on this side. When doing so, you had the weight of the object divided by the electrical field strength. That was the calculation he did, and his goal was to try and find, this is an equation we'll use, his goal was to try and find the charge of a single electron. Unfortunately, and this would have upset and infuriated me to the point where I probably would have quit, Millikan found that absolutely none of his values for Q were ever the same, trial to trial, and he did probably hundreds of trials. I know I did hundreds of trials just on my own research in college. The research project we had to do just to graduate took me 9 months. I did hundreds of trials, and I wasn't trying to find the charge of something so fundamental to our understanding of the universe. I was literally just trying to find out what was inside the solutions that we made. Anyways, my point is, none of his trials lined up, but what he did eventually realize, he didn't have computers at this point, what he did eventually realize was that every single one of those numbers was a multiple of this. He literally went back to old school algebra, and he found the least common multiple of all of the values that he had gathered, right? Basic algebra for the win. He found the least common multiple, and that least common multiple right here is the charge of a single electron. It is the charge of a proton and the charge of an electron. It is the fundamental charge of every particle we've ever talked about. And so if you had 4 of those, then it's literally 4 times that number. If you had 5 electrons, it's 5 times that number. 100 electrons, it's 100 multiplied by that number. That is the charge of an electron. And that's how he found it. He literally got that little oil droplet to hover motionless in the air. And he knew how much electrical force he applied to do that. He turned the machine off, let it fall onto the bottom plate. The bottom plate was attached to a scale. He found the weight of that oil droplet that had been hovering there. It was pretty cool. It was a pretty awesome experiment. Anyways, that was your notes. We're going to go into assignment 2 together in class the next time I see you guys. And I'm going to be making a video for assignment 3, charging by conduction and induction, just because it's a weird concept, those charges and how they move. So I'll be making a video for assignment 3 for you guys here in a little bit as well. So that was about it. Let me know if you've got any questions, comments, or concerns. This video did not give you all of the values and all of the information that you're going to need for the reading note quiz, but it did give you quite a few, and I'm hoping it was a good start. Please, 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 as always, don't hesitate to reach out with questions or concerns.